Today we are focusing on a seemingly simple yet incredibly critical aspect, the size of the material charged into blast furnace, also known as the burden input size. The size distribution of these materials not just a detail, it's a key parameter for proper operation. It significantly impacts the particle size distribution within the furnace bed inventory and the solid concentration, which in turn directly affect crucial processes like gas flow, heat transfer, and temperature uniformity. Coming to our next slide, which is a most important slide. This is about, let's talk about the coke. Coke isn't just fuel, it's play a multifaceted and vital role in blast furnace. It provides heat, reducing gases, support for the entire burden column, and crucial permeability for both gas and liquid flow. When we consider blast furnace coke, which is the main charge, it's typically added as 50 to 60 diapieces. The average size I would expect to see it generally around 45 to 55 However, specific requirement can vary. Some furnaces might use coke with a grain size range of 20 to 75 or even larger pieces such as 60 or more, which term as a sinter coke. For instance, a smaller blast furnace coke particle diameter is recorded as a 57 while much larger foundry coke can approach around more than 120 150. The key takeaway here is that well-sized coke is absolutely essential for permeability, allowing gases to travel up efficiently and molten iron and slag to drain away. Now, coming to our next slide, which is about our nut coke. That is, we can say that beyond the main blast furnace coke, other fraction like nut coke also plays a very important role. We have nut coke, often called a small coke, which typically range from 6 to 25 This is added with the ferrous mineral layer in the blast furnace and can replace some coarser coke. A small size coke around 20 in average particle size, ranging from 5 to 25 we can say, can even be mixed into iron ore to improve permeability and reduction efficiency. Then there's coke braze, which is defined as a material less than 6 These finer materials generally not used directly in blast furnace but is typically employed as a fuel in sintering or pelletizing plant. Lastly, we must consider coke fines which are generated right inside the furnace. During descent and reaction, coke inevitability degrades, leading to the formation of these fines. The upper limit of coke fines that can pass through the coke packed bed is estimated to 3 to 5 In the highly active raceway area of the blast furnace, the amount of fines that is less than 3 or 5 can quite significant, reaching 25 mass percent for less than minus 3 to 40 mass percent for less than minus 5 And crucially, these fines can severely inhibit gas permeability. Now coming to moving on to the iron bearing material, sinter is a key ferrous charge material produced from fine grain iron ore. When it's charged into the blast furnace, the size of sinter typically range from 5 to 40 with a mean size of 15 to 25 after the sinter plant. The harmonic mean diameter of sinter is typically 14 However, sinter is prone to degradation during transport and handling, so it's rescreened at blast furnace to remove fines before charging. These sinter fines are defined as material less than 6 It's particularly important to control these as a fines smaller than 5 are especially detrimental to the ore layer permeability. Next, we have a pellets which are agglomerated iron ore material, notable for their narrow size distribution. These are typically small balls formed with a diameter of 8 to 16 ideally between 80 to 90% of pellets should have a dia of 15 mm, with the majority falling between 9 to 12 mm. It's strongly recommended that the charge contains neither fines defined here as a less than 5 mm nor pellet exceeding 25 mm in diameter. Some suppliers achieve impressive uniformity with 94% of pellets between 9.5 to 14 mm. One of their key advantages is that their ability to remain intact in the blast furnace, contributing to stable burden permeability. Like sinter pellet fines are an issue, fines again defined as a less than 6 mm are screened out at the stockhouse. Interestingly, the raw material for pelletizing known as a pellet feed are extremely fines down to 80% passing to 45 micromillimeters. Now let's discuss pulverized coal injection or PCA coal. This is pulverized coal injection directly into blast furnace as a reductant. Compared to other burden material, PCA coal is exceptionally fine. Typical pulverized injection coal has an average particle size of 150 micromillimeters for every specific application such as cyclone fired burners. Coal samples might be pulverized even finer to about 90% less than 138 micromillimeters with an average particle size of 45 micromillimeters. Even finer anthracite coal tested in an earth boiler had mean size of just 37 micromillimeter. Clearly, for successful injection, coal must be meticulously crushed or ground. A byproduct related to PCA is unburnt carbon or which refers to fine particles resulting from PCA that are not fully combusted. This unburnt particle can be spherical and possess a remarkable large specific surface area ranging from 10 to the power 4 to 10 to the power 6 square meters per kilogram. So we are coming to this slide, which is about the fines repeatedly are coming in the system. Gas flow resistance is greatly influenced by the ratio of small and large particles. This is because the smaller particle can fill the voids between the larger ones, drastically reducing permeability, as we all know fundamentally. Therefore, controlling fines, which are typically defined as less than 5 mm, is absolutely crucial. If left unchecked, these fines tend to concentrate in rings within the furnace, effectively blocking hot reducing gases, and this can lead to significant operational problems such as formation of scabs on the furnace wall or an increase in required fuel rates. To combat this, screening of raw material at stockhouse or stockyard is essential. To remove these fines, typically sieve size used for measurement include 6.3, 8, 16, 22 and 31 millimeter. It's worth reiterating an excessive amount of fines, specifically those less than 5 mm, can dramatically increase resistance to gas flow. Now, given the detrimental impact of fines, what are the strategies for managing them effectively is a great question. One key strategy to controlling material is controlling material moisture. Once we dry out the material, then screening out the fines has become very easy. So dry material is screened much more efficiently than wet material, and wet lump pores, for instance, can carry piggyback fines that adhere to larger particles, making proper screening difficult or even impossible. Reducing moisture content is therefore crucial for effective screening. Proper screening practices are also paramount, and it's standard operational practice to use a screen with a 5 mm aperture before charging burden material into blast furnace. Rather to the specific, that should be a 6 mm. Both coke and ore burden are typically screened in the stockhouse just before the charging to remove fine material. The target for fines after screening in the stockhouse should be less than 3 mm, 3%, that is below 5 mm. Careful bin management in the stockhouse can also prevent fines generation by filling bins gradually or operating with the fewer bins to increase level more quickly. You can avoid material falling long distances and breaking down, thus reducing the generation of fines. For optimizing coke screening, the primary objective is to remove fine coke. Typical specification after screening aim for a maximum of 2% smaller than 25 mm or a maximum of 3% smaller than 30 mm. While coarser coke screening can improve permeability, it also produces more nut coke or small coke, which is then added to overburden layer. Finally, improving burden distribution is vital. Distributing fines effectively across the furnace radius, potentially by using a large number of chute positions, um, hmm, 7 or more, we can say, for the ferrous burden is important. This helps to mitigate the negative impact of fines on gas flow. Now, what happens to the fines particle that do make it through or are generated within the furnace? The top gas leaving the furnace, blast furnace contains solid particle and is typically sent for dedusting and demisting, while specific particle sizes for dust catcher output are not detailed in our sources. The process aimed to capture fine soot and carbonaceous material using cyclone and filters. Regarding gas cleaning system, the sources refer to gas cleaning and gas washing of blast furnace top gas to remove fine particle, but no specific particle size targeted to present within the scrubber itself are provided. Similarly, for a clarifier, no specific particle size information for material is provided through clarifiers typically handle very fine suspended solid and liquid streams, often an output of wet gas cleaning. Finally, the sources mentioned BF dust and sludge as the material that are recycled back into the sinter blade. These indicate these are the fine material through no specific particle size or size range is given for sludge also. Now coming to the power of particle size control, as we know that the journey through the various particle size in the blast furnace operation highlight one overreaching principle. The effective management of particle size distribution, especially the rigorous control of fines, is absolutely paramount for optimum blast furnace operation. Proper sizing of all material ensure good permeability, facilitate uh, efficient gas flow, and lead to a stable furnace condition, thereby preventing operational problems and significantly improving overall efficiency.